Good afternoon, everybody. Welcome to lecture. Thanks for coming. It's Monday, and I have a couple of announcements. First of all, Canvas is not working, hasn't been working for a while. The survey on Canvas, therefore, will be extended. I don't know when Canvas is going to come back up, but when it does, I'll give you a good, healthy amount of time to do that survey question. All you have to do is click in an answer, look at the question, submit an answer, and then you'll get credit for it eventually. It was a naming question, so we've talked a lot about naming. I thought it was a pretty easy one, so I think you're going to be fine with it. But anyway, that's some news. Exam 2 is coming up next Monday, so that's kind of the big announcement. And it is going to be in class on Monday, and it's going to cover the things that we've talked about since the last exam, and that includes radical reactions from Chapter 13, conjugation and Diels-Alder reaction from Chapter 14, aromaticity, which is the stuff we're talking about now, and then carboxylic acids, some select items out of carboxylic acids, and I can't remember what chapter that is because I don't have the syllabus as a Canvas, so I can look it up, but it's like I can't look it up right now. Carboxylic acids, we're going to talk about that Wednesday and Friday. So that's what's coming up. If you have any questions about the exam, let me know. There's a module in Canvas when Canvas is available that lists all the things that is associated with exam 2, like support materials that you're going to get, reference materials, and details about the exam, and some molecules of the day. And I have a molecule of the day for you that I wanted to share. It's an interesting one, and it's got some aromatic rings in it. So here's today's molecule of the day. This one is called, the name is ibrutinib. That's the generic name. The brand name that it's sold under is Imbruvica. It's an anti-cancer drug. So it was first approved in 2013 for a particular type of cancer, and then was expanded for other uses too. It's a broad spectrum anti-cancer drug that is effective against a lot of B cell lines. So if you have a cancer that's malignant B cell type, this might help treat it. It affects a signaling pathway that they need to survive. So there's an event, a signaling event called a phosphorylation event, and that's catalyzed by a type of enzyme called a kinase. So a kinase is an enzyme that puts a phosphate group on a molecule. Well, that's an important step in the survival of these kinds of cancers. And so if you can knock out the enzyme that does that, then you can slow the growth of that type of cancer. And that's what this does. That's what this molecule's trick is. And so it has this structure that looks like this. There's a 6-membered ring that's got a couple of nitrogens in it and alternating series of double bonds and single bonds. There's a nitrogen over here. And then down here, there's a 5-membered ring that's got a couple of nitrogens in it as well. And attached to the nitrogen is a 6-membered ring. And that 6-membered ring has a hydrogen here on a wedge bond. There is a nitrogen in this ring over here. And that nitrogen has a carbonyl and then a vinyl group. And then over here, on this side of the molecule, there's another aromatic ring that has an O bonded to yet another aromatic ring here. So lots of aromatic rings, some that are somewhat familiar and others that are kind of weird and new. Let me go through and talk about a couple of them. So we got benzene ring here, benzene ring here. Those are definitely aromatic rings. Then we've also got a ring here and a ring here. This whole ring system actually is another example of an sort of exotic aromatic ring. We're going to talk about today focusing on how heteroatoms impact pi electrons. In other words, how do you count pi electrons in this molecule? There are nitrogens that have lone pairs that are both outside of the ring here and here, but then there's lone pairs on nitrogen here, nitrogen here, nitrogen here, nitrogen here, and nitrogen there. And we got to develop some theoretical framework for understanding which ones of these are pi electrons and count towards determining whether the molecule is aromatic or not. And so it's a big focus of today's lecture. The other thing that we're going to learn about is when are nitrogens basic? and when are they not basic. And so I'm just going to go through and highlight some lone pairs, and I'm going to say this nitrogen right here is basic. In other words, that lone pair can be shared with an acid, and it can abstract a proton off of an acid. It's also a really effective hydrogen bond acceptor because it's got a lone pair that's really available. This is also a basic nitrogen. That lone pair, I should probably circle the whole nitrogen just to indicate that it's like that. All of these that I'm circling here, these are all basic nitrogens. These are all ones that will accept an acid. And then there's two nitrogens in this molecule that are not basic. This one right here in the ring system, that is a non-basic lone pair. So I'm going to say right here, not basic. This one is not shared really under any circumstances. The molecule does not want to give up that lone pair. I'm just going to draw it a little bit more crisply here so it's really clear. It's a pair of dots. The other one that's not basic is this one over here on that nitrogen. And so why are some nitrogens basic and others not? There's two reasons for this, and we're going to spend some time talking about this. I'm going to say that in general, nitrogen lone pairs are usually basic. I'm going to say are often basic, because it really kind of depends on what nitrogen you're talking about. On amino groups, for example. So this is an example of an amino group right here. That's a nitrogen that's attached to something with a lone pair, and that lone pair is available to be shared with acids. Some exceptions, though. Exceptions. When a nitrogen lone pair is not basic. Condition number one is when it is an amide nitrogen. So this is an example of an amide nitrogen right there. The amide functional group has a nitrogen with the lone pair, but that lone pair is not all that available for sharing to acids because it's already being shared with the carbonyl oxygen. In other words, what you can do, you can draw a resonance structure where you start an arrow on that lone pair and you push it this way and you push it up onto that oxygen. And that set of resonance structure arrows is saying that this oxygen already has ownership of a lot of that lone pair. So that lone pair is not just on nitrogen, it's shared with oxygen. So nitrogen isn't able to give it away because it doesn't really own most of it. So that one is not available for sharing. Amide lone pairs are not basic. The other situation, the one we're going to talk a lot about today, is when the nitrogen lone pair is part of a pi system making a ring aromatic. So we talked last time about how certain numbers of pi electrons lead to a ring being aromatic and really stable. So if a molecule a ring is really stable because it's aromatic and you try to give 2 of its pi electrons away, it'll no longer be aromatic, and that's going to be energetically really expensive. The molecule is really stable with a certain subset of pi electrons, and those are not available for sharing, even if they're a nitrogen lone pair. So that is the basic idea. And it just so happens that that lone pair right there is needed to make this ring system aromatic. And if you're counting pi electrons, the way that this ring gets to aromatic is you count 2 for every one of the double bonds. So there's 2, 4, 6, 8. And then that lone pair gets you to 10. And 10 is a 4n plus 2 type system, and that makes this ring system aromatic. The nitrogens that are basic, that are in the ring and basic, those are not pi electrons, and so those aren't critical for making this ring system aromatic, and the molecule doesn't really need them to be really especially stable, so they're free to be given away. They're available for sharing, basically. So we're going to talk a lot about that today, and that's where we're going to start the lecture. So any questions, though, about the molecule of the day? It's an interesting one that shows a lot of really important nitrogen behavior and interesting molecule therapeutically, too. So, all right, let's talk about heteroaromatics some more then. We got started with this discussion last time when we were talking about pyridine. And pyridine was a 6-membered ring that had a nitrogen in it. It looked a lot like benzene, but benzene where one of the carbon atoms was replaced by nitrogen. So I want to put that one back up here just for reference so we can use it as a starting point for our discussion today. So pyridine looks like this. It's got a 6-membered ring with 1 nitrogen in it, and there's a series of alternating double bonds and single bonds. And the way that the orbitals work in this molecule, and I'll draw a side view of pyridine that is going to try to indicate what's going on with these orbitals, is there's p orbitals on every atom because every atom in pyridine is sp2 hybridized, including the nitrogen. There is the lone pair on nitrogen is in an sp2 orbital. And then the p orbitals are here. I'm going to draw them in orange again just because that's kind of the system I've been using, just to distinguish them from hybrid orbitals. So these are the p orbitals. There's the upper lobe of the p orbital on nitrogen. There's the lower lobe of the p orbital on nitrogen. And the nitrogen is using that p orbital to make a pi bond to its neighboring carbon right here. And then because this p orbital is right next door, it's also overlapping with that one. And basically all the p orbital lobes overlap in this molecule. And so it's got these 2 donuts of electron density, just like benzene does. The orange represents the overlapping pi system. It's a complete circuit of overlapping p orbitals. And the electrons on the nitrogen aren't in that pi system. These aren't pi electrons. So I'm going to say that not pi electrons. These can be shared without affecting aromaticity. So this ring is aromatic because it has 6 pi electrons. There's 2, 4, 6 in the pi cloud from those double bonds there. And if you wanted to put them on the graph in a special, in a particular spot, 2 electrons there, that's what we think about when we think about a double bond between 2 atoms. Then there's another double bond here. I'll just draw a pair of electrons there to account for them. And then there's a double bond here that I'll put a pair of electrons in here. So these are the 6 pi electrons. It's not like they're localized in that spot. They're not just sitting there. They're moving throughout, and they're spread out throughout the whole overlapping p system. But this is a good way of accounting for them. There's 6 here, and then there's 2 more here. And these are outside of the pi system, though. So 6 pi electrons, and that's a 4n plus 2 system. So that's why this is aromatic. And if you gave that lone pair away, it would still be a 4n plus 2 system. So in other words, pyridine can pick up a proton and become this molecule, which is called pyridinium cation. Now the nitrogen has a plus charge, but you know what? It still has 6 pi electrons, 2, 4, 6. So we didn't break the aromaticity of this ring by putting a proton on it. So, and this is just fine. So this is aromatic. And this down here, this protonated version, is still aromatic. So that's why that lone pair on that nitrogen is basic, because it doesn't affect aromaticity. It's not involved in aromaticity. That's pyridine. Not all nitrogens are created equal, though. Sometimes it does matter. And maybe what I'll do before I move on is I'm going to show you this diagram that I have here, this model kit that I have that tries to show these orbitals. So this is the pyridine. Here's the pyridine, and I put this green lobe with the dots on it to represent the lone pair on the nitrogen here in this sp2 hybridized orbital. So if you turn it on its side, you can see the p orbitals, the overlapping p orbitals are these lobes on the top. There's overlap here, here, and here. There's also overlap between the atoms, even in the spots where we don't have the white, like plastic bent bonds. It's a ring of electron density. And the important thing is there's 2, 4, 6 pi electrons in the ring, and then 2 that are outside of it that don't count as pi electrons, because they're in an sp2 hybridized orbital right there. All right. But sometimes it's a little different, and that's what we're going to look at over here. So I'm going to introduce another nitrogen-containing molecule that behaves very differently. This one's called pyrrole. Pyrrole is, just want to make sure I draw it my favorite way to illustrate orbitals. It looks like this. It's a 5-membered ring with a nitrogen in it. It goes nitrogen, double bond, single bond, double bond, single bond. And then the question is how do you count electrons in this system? You get 2 for every one of these pi bonds. Here the nitrogen lone pair counts, and let's try to figure out why that is. So first of all, I want to remind you of the XYZ rule. We looked at this in a previous chapter. It was a rule that said if you have a system that goes XYZ, where you've got any atom X double bonded to any atom Y and then single bonded to Z where there's a lone pair on it, then this atom is sp2 hybridized, and lone pair is in p orbital. So that's describing this nitrogen exactly. That nitrogen is sp2 hybridized, and that lone pair is in a p orbital. sp2 lone pair in p orbital. If I draw it in a molecular orbital picture, it'll become clear exactly why this is doing what it's doing. So here is the pyrrole molecule in a side view. And since nitrogen is sp2 hybridized, I'm going to draw a p orbital on it. I'm going to put the lone pair in that p orbital, because that's where it goes. Then we've got p orbitals on our other atoms in the pyrrole ring. based on the picture, the classical picture of Lewis structure and the bonding of this, there's double bond there, double bond here, with a pair of pi electrons. And so this is how we're getting 6 pi electrons. We've got 2 for every one of the carbon-carbon double bonds, so that gets us to 4. And now the electrons here, they count because this is a p orbital. And they are in this overlapping system of p orbitals, and the electrons are shared in this pi system. So Parole has 2 donuts of electron density just like benzene and pyridine. It's just that the nitrogen is needed to contribute its lone pair in order to make that happen. So these are pi electrons now. So here, the nitrogen lone pair is in the pi system. It contributes to giving the molecule 6 pi electrons. And being a 4n plus 2 system, which is aromatic. So it's a bunch of words to say that that lone pair is needed for aromaticity. The ring needs that. The ring will not share that lone pair of electrons if it's life dependent on it. If you try to protonate Parole and you put in one of the strongest acids you can think of, it doesn't even protonate here. It protonates over there. Shows you how much this molecule really doesn't want to give up that lone pair. So in this case, this nitrogen lone pair is not basic because it's needed for aromaticity. If you were to give that lone pair away, this ring would go from being really stable and aromatic to a lot less stable, non-aromatic, and that's an energetic price that the molecule is not going to pay. It's just going to say, no, can't have my electrons. I need them. I want to be aromatic. Doesn't say, obviously, you know, anthropomorphism is sort of a common thing that we do in chemistry to try to understand these molecules, but that nitrogen is like really wants to keep those electrons in its lone pair. Okay, any questions about that example? And I can, I'm going to just build a real quick model of this one to show you what that looks like in terms of molecular orbitals, because sometimes the pictures are helpful, but they don't always communicate every bit of, you know, the structure. So here is.
Would that pi bond or that those lone pair be weaker than that one because it's part of the pi?
Let's see. So the question is about this molecule, and you're asking about that lone pair.
Yeah, would it be weaker than the other one because it's not a part?
It is more shareable. So so I'm going to direct the camera over here to just make sure I've got a picture. So the question is about that lone pair. It is less tightly held by the nitrogen. So the nitrogen has no like real strong desire to keep it. So so an acid, it would share it with an acid. So if an acid comes along in H+, the nitrogen is okay donating it to the H+. The other molecule, the nitrogen is not willing to share because it just costs too much. Just causes it to become no longer aromatic. Okay, all right. So I'm going to build a model of this Parole molecule, and we're gonna just look at it very briefly to make sure that we can understand what a structure is. And Make sure it's crystal clear exactly what's going on with the orbitals. If I can get it apart. Here we go. Okay, there we go. So this is the parole. Change the view on the camera. So this is the parole molecule, and it's got p orbitals here, which I'm showing in blue. And if you turn it up like this, the p orbital is lined up parallel with the p orbitals in the overlapping pi system of the carbon-carbon double bond. So they together form a ring of electrons, and you just have to imagine that the nitrogen contributes 2 pi electrons. 2 pi electrons in this p orbital contribute to the 6 total for the ring. All right. Let's look at an example that's got a couple of things going on at once. So the thing about these patterns is that you see them all over the place. And the one that I'm going to show you now is one that's a really important ring that occurs in biology. This is a molecule that's an aromatic ring that's called histidine. Imidazole, sorry. It's present in the amino acid histidine. So it looks like this. It's got 2 nitrogens in it. And the way I'm drawing it is the one on the left over here has a lone pair. The one on the right has a lone pair, and there's double bonds in the ring like this. This is called imidazole. That is the side chain in the amino acid histidine. It's also one of the key components of the signaling molecule histamine. So if you're struggling with seasonal allergies right now because it's fall and there's a lot of pollen, you can thank histamine, this signaling molecule that induces an allergic response. And this molecule is part of it. There's like a couple of carbons and a nitrogen at the end, and that's histamine. So what's going on with this one? Well, it's got features that mimic both pyridine. It's kind of like pyridine on the left side and kind of like parole on the right side. It's got both kinds of nitrogens. This one is non-base. This one's basic. This one over here is not basic. I'm going to draw an orbital diagram of it to try to indicate what's going on. So this is going to be an edge view of the imidazole molecule. There's a nitrogen on the left and a nitrogen on the right. Nitrogen on the right has a hydrogen on it. And then every atom here is sp2 hybridized. I know that nitrogen is sp2 hybridized because it's part of an XYZ system, or XYZ. You can figure it 2 different ways, see it, observe it 2 different ways, the way it fits the XYZ pattern. So it's sp2 hybridized. It has a p orbital, and that's contributing a pair of electrons to this pi system. We've got nitrogen, other nitrogen on the other side is sp2 hybrid as well, has a lone pair, but this lone pair is in an sp2 orbital. It doesn't count as pi electrons because it's not held within the pi system. And then there's overlap between orbitals, p orbitals. Like that mimics the Lewis structure that I've shown here with, a pi electron, a couple of pi electrons shared here. And then we know now, because of what we know about resonance and conjugation, that they're sharing throughout the pi system. All the p orbitals are sharing electrons. And so all 6 of these electrons that are held in the pi system are shared. So you can get to 6 pi electrons by counting 2, 4, 6. So this is an aromatic ring. The lone pair on the left is not needed for aromaticity. It's not in the pi system. The one on the right is. So this molecule, when it is an amino acid that's on a protein that's catalyzing a reaction, that would be a nitrogen lone pair that would be very basic and would participate in like proton transfers, grabbing a proton and then giving it back. This one really would not. So it's important for how it behaves. So that's imidazole. Yeah, question. Yeah, so the question is does the XYZ rule determine whether it's basic or not? What I would say is the XYZ rule is a quick way to identify when it will be basic or not. The way I would explain this is that the molecule has this arrangement of orbitals and electrons that makes it really stable. So what the molecule doesn't obviously know about XYZ rule, but what it does know is that, hey, if I flatten out and this nitrogen becomes sp2 hybridized, and I put that lone pair in a p orbital, I'm going to become really, really stable as an aromatic molecule. So the molecule, the atoms arrange their electrons in the orientation that gives them the most stable possible arrangement. And with this molecule, that being sp2 makes it a lot more stable because then it's aromatic. So essentially, it's the molecule trying to achieve its lowest energy state. And if it were sp3 hybridized, for example, there wouldn't be a p orbital to overlap. It wouldn't be fully conjugated, and it wouldn't have this aromaticity benefit. So it doesn't want to be sp3 hybridized because that's higher in energy. It becomes sp2, then it can all of a sudden contribute to an aromatic ring. So it's overall a low energy way of existing. So the reason that electrons arrange themselves the way they do around an atom is to give the lowest possible energy. So a lot of times it's all about just electrostatics. 4 electron groups wanting to be far apart, they adopt a tetrahedral arrangement. In this case, though, there's a benefit to not being tetrahedral. There's a bigger benefit to being sp2 hybridized and being trigonal planar, because then it gets to be aromatic. So they'll like settle into whatever geometry is the best for them in terms of energy. So yeah, it's kind of a complicated explanation, but a quick way to check for this is anytime you have a nitrogen with a lone pair on it that's part of an XYZ system like this, then that is a sp2 hybridized atom, and that lone pair is in a p orbital. Let's look at an oxygen example. So oxygen is another heteroatom that is found in many rings. And let's see how it behaves when it's in a ring that could potentially be aromatic. So I'm going to give you a molecule now called furan. Furan looks really similar to pyrrole. It's just an oxygen variant. So if we were to just replace nitrogen or oxygen with nitrogen, that would be pyrrole. So all I did was just change heteroatoms. So let's see if we can figure out what's going on with this molecule orbital-wise. Like, where are the electrons? What kinds of orbitals are they in? So let's just take a moment and apply the XYZ rule if we can. So what do you think about that oxygen? Is it part of an XYZ system? Yeah, I can go XYZ here, where I go atom double bonded to another atom, single bonded to an atom that's got a lone pair. This fits the X, Y, Z pattern that we've been looking for. So the Z is sp2 hybridized, and electron pair is in a p orbital. Now this one's got 2 electron pairs, so that's a little bit of a puzzle at first, but there's only space for 1 lone pair in the p orbital. So if there's 2 lone pairs, one of them is in a p orbital, the other one has to be someplace else, and it's going to be in an sp2 orbital. So what I can tell you about this molecule right now is that oxygen is sp2 hybridized. And 1 lone pair is in a p orbital, the other is in an sp2 orbital. And I'll draw a picture of it to try to illustrate how that works. So the oxygen is sp2 hybridized. It has a p orbital. It's got 3 hybrid orbitals, 3 sp2 hybrid orbitals. It uses one of them to bond to that carbon. It uses the other one to bond to that carbon. And then the third sp2 orbital is right here, and that holds one of the lone pairs of electrons. The other pair of electrons is in this p orbital right here. I'm drawing them in the top lobe. They're really both equally shared between top and bottom lobes, but when you draw them as discrete objects, you have to put them someplace. Just for accounting purposes, I'm going to park them here for now, but in reality, they're spread out over this whole p orbital, and then further shared with the whole pi system. So the pi system in furan is that the other atoms, the carbon atoms, all have p orbitals, and they have overlap. The Lewis structure picture has carbon-carbon double bonds in it that contain a set of pi electrons, 2 pi electrons each. So here's the picture of the molecule. You get 4 pi electrons from the carbon-carbon double bonds, and then you get to 6 from using one of the lone pairs on the oxygen, and the other lone pair is held outside of the pi system. So these are pi electrons. These are used for aromaticity. So the molecule has 6 pi electrons, and it's a 4n plus 2 system as a result, and therefore it's aromatic. These electrons right here are outside of the pi system. These are not pi electrons. They're more shareable. Oxygen isn't basic the same way that nitrogen is basic, but if this molecule were going to share a pair of electrons, that would be the pair that it would share. It's Lewis basic. It'll share a lone pair to something that's like got a positive charge, and those are the ones that are most shareable. These are not. And the full picture of the thing is that all of the p orbitals overlap to yield the 2 donuts of electron density above the plane of the atoms and then below it. So another aromatic molecule. Looking good. So furan, you get these oxygens appearing in aromatic rings in a bunch of different places. So that's an example of oxygen. You could plug a sulfur in here, and since sulfur is right below oxygen in the periodic table, they behave like almost exactly the same way. So sulfur and oxygen, in terms of aromaticity, are basically interchangeable. They behave the same way. I could put a sulfur here, and then over here it'd be a sulfur with a p orbital and an sp2 orbital holding its 2 electron pairs. Question?
So will we need to say if that oxygen is basic or not? Because if we did, what would it be?
Yeah, I won't ask you that question. What I might do is point to a pair of electrons in an orbital diagram and ask you which of these are pi electrons, for example, because it isn't basic in the same way that nitrogen is, so it's not gonna be a question that you'll get asked you're not gonna get asked that question. So, yeah. All right, well, let's take a quick look at some other, just a few other examples, just to highlight the diversity in the aromaticity patterns that you'll see. Important biomolecules, for example. There are examples out there of all sorts of combinations of different kinds of heteroatoms and different kinds of rings. Here's a few that are really important. This is a really important aromatic ring that incorporates a couple of different rings. This is an aromatic system. This molecule is called indole. And it's the core kind of important heterocycle that's part of the side chain of the amino acid tryptophan. It's also important in there's an important neurotransmitter called serotonin, and this is like at the heart of the serotonin structure is this molecule. And there's some substituents and things, but that's a big part of it. But the way this behaves is it's like a benzene ring on the left side and like a parole ring on the right side. And for counting electrons, you want to count all of the double bonds, counting 2. So you get 2, 4, 6, 8. And then in this case, because the nitrogen is part of this XYZ system, that lone pair is in a p orbital, contributes to the pi electrons. So you count this lone pair as pi electrons, and that gets you to 10. So this molecule has 10 pi electrons. And that's a 4n plus 2 type system. And it is aromatic. All right, let's look at another one here, another molecule. This molecule is called oxazole. It's present in a lot of important pharmaceuticals and other things. Occasionally a biomolecule will incorporate an oxazole. It's got a nitrogen and an oxygen. So on the right side here, it kind of behaves like furan in that one of the 2 lone pairs is in a p orbital and counts as pi electrons. This one behaves a little bit like pyridine in that that lone pair is not pi electrons, it's in an sp2 orbital. So for pi electrons on here, you count 2, 4, 6. And the nitrogen lone pair and one of the oxygen lone pairs are not included in that count. So this one's got 6 pi electrons. That's a 4n plus 2 system. And therefore, oxazole is aromatic. All right. Heteroatoms are interesting, but it's not the only interesting wrinkle in aromatic chemistry. We also need to talk about charged molecules. So this is the last kind of detail with identifying aromatic, anti-aromatic, non-aromatic molecules, and that sometimes you get atoms within the ring that bear a charge. And so we're going to talk about how to handle those. Here's an example of a charged molecule. So it's got 7 points. There's 7 carbons in it. It's not the best 7-membered ring I've ever drawn, but what it does have is an alternating series of double bond, single bond, double bond, single bond, double bond, and then there's a carbon that has a positive charge. So remember about carbocation carbons, they're sp2 hybridized, so that's an sp2 hybridized carbon, and there's a p orbital there. So this is a fully conjugated system. It's got overlapping ring of p orbitals. And then how do you count pi electrons? Well, if there's a positive charge there, that means that there's no electrons on that no lone pairs of electrons on that carbon. So there's just none that are contributed there. So we count 2, 4, 6, 2 for every one of the double bonds. So this molecule has 6 pi electrons. And it's a 4n plus 2 system. And it's aromatic because it meets all the criteria. It is a ring. It is flat because 7-membered rings can be flat. It's fully conjugated when it's flat because every single one of the atoms has a p orbital that can overlap when it's flat. And then you put 6 pi electrons in there and you get an aromatic ring. So this molecule is called tropylium ion. It's a special name for this molecule that is just, it's an example of a charged aromatic species. And the plus charge is delocalized onto every single atom on here. So it's not like it's stuck like that. So sometimes you'll see tropylium ion drawn like this, where it's a 7-membered ring with a circle and a plus inside of it, just to indicate that the plus charge is like delocalized throughout the system. You could draw resonance structures where you push electrons like this and put the positive charge there, put it there, and then and essentially through a series of resonance structures, you can drop it onto every single carbon on the molecule. So it's a really highly delocalized positive charge. Okay, let's look at another kind of example of this. Let's take a look at this one. Actually, I'm going to give you 3 examples. To think about. So they're all 3-membered rings with 1 double bond in, and then they've got something going on here. This one has a positive charge. This one has a dot. This one has a negative charge. So if we think about hybridization here, carbocation carbons are sp2 hybridized. So that is a p orbital right there, and p orbitals elsewhere on the molecule. So this has a full ring of p orbitals, and it's flat because this molecule is really small and rigid. It cannot wiggle out of planarity just because it's just too rigid, even if it wanted to. What do you think about pi electrons in this one? How many would it have? 2, yeah, because it said 2 because it's got 2 from this bond and none from that. So this has got 2 pi electrons, which actually fits the 4n plus 2 rule, where n is equal to 0. And so this one's aromatic. That means that this little ring is way more stable than you would expect, and it's much easier to produce it than you might imagine. It's still got a double bond in a 3-membered ring, which is a tough situation because 3-membered rings have 60-degree bond angles roughly, and sp2 hybridized atoms like to have 120 degrees. So it's still got some angle strain, but the electronics of this one make it for a really favorable kind of situation. This one has got a carbon that's a radical carbon. If you remember back to chapter 13, carbon radicals are sp2 hybridized. So that dot is in a p orbital. So this one has 3 pi electrons, which is not a number that fits either the 4n or the 4n plus 2 rule. So this one is just non-aromatic. It doesn't fit any one of the rules as far as pi electrons go. And then this one is part of an XYZ system. You've got X, Y, Z, where that atom is sp2 hybridized. The electron lone pair is in a p orbital. So they count as pi electrons. So this one's got 4 pi electrons. And this is a 4n type system. and it would be anti-aromatic. That molecule will be really unstable. And it's really hard to make. When I was in graduate school, one of my grad school friends, her thesis project was making this, and the way she had to do it was to make it and study it in the gas phase, because if it ever formed, it would just want to react with whatever it was near immediately to try to become no longer anti-aromatic. So they had to use some special tricks to try to generate it and then to study it before it disintegrated. But it's a real species. It's just really unstable. And that's some examples of charged species. You could look at other charged species. Let's go take a look at another ring size. One of the things I want to be careful of is that you don't always equate positive with being aromatic, because sometimes you got to look at every single individual case. So I want to share another example with you, just so you don't like accidentally try to find a pattern that isn't there. Here's a molecule that is a 5-membered ring that has double bond, single bond, double bond, single bond, and then there's an atom here that's a carbon atom that has a lone pair and a formal minus charge. That's one Lewis structure of it, one resonance structure. These count as pi electrons because it's a part of an XYZ system, and that carbon is sp2 hybridized, that lone pair is in a p orbital, and they count as pi electrons. So when you count these, you count those as pi electrons, so you get 6 pi electrons. And that is a 4n plus 2 system. So that's an aromatic ring. And it's got a special stability. So sometimes you can get, basically all these molecules are going to be variations on themes like this. So I think you've seen enough of them now that you could probably follow the pattern in whatever kind of molecule you might get. But let me go through a couple of examples with you just to try to just make sure it's clear and cemented in your head, and that as the molecules get bigger, they don't necessarily get more complicated. They might get more pi electrons, but that doesn't make them harder to figure out necessarily. So here's a molecule that I wanted to call your attention to. It's got this pattern. And I should make this a little bit, this angle a little bit better here. Do that with it. Okay, and then I've got alternating series of double bonds, single bonds, and a positive charge right there. All right, looks weird. But let's just treat it like we've treated all the other molecules we've looked at. Recognize that every one of these carbons is sp2 hybridized, has a p orbital. Carbocation carbon is also sp2 hybridized, it has a p orbital. So this molecule is fully conjugated when it's flat. So then I guess the question is does it want to be flat? What would happen if it were flat? How many pi electrons does it have? Let's think about the consequences of being flat. So the molecule's got, if we count up all the pi electrons, 2 for every double bond, we get 2, 4, 6, 8, 10. That is a 4n plus 2 system. It's a big molecule, so it could be flat or puckered. It would be aromatic when it's flat. If it were puckered, it would be non-aromatic, which is higher in energy and less preferred. So this is the the way it wants to be, you would predict that this molecule would be flat, because that's the most stable conformation for it, because that makes it aromatic. Now, if there were a lone pair and a minus charge here, being flat would make it anti-aromatic, because then it would have 12 pi electrons, not 10. So the anion version of this would definitely want to be puckered, because that's non-aromatic and that's better than being anti-aromatic. So, and there's sometimes there are versions of this that mix a couple of different things. So I want to show you one example that I found in some old problems that I had. It's a molecule that looks like, I'll have to put the structure up here. Oh, that wasn't it. Here it is. Actually, I think it was a homework question. I'll just invent a new version of this to talk about. It's basically the same molecule, except I'm going to substitute a nitrogen in place of one of the carbons. So then I guess the question is well, and I better put a double bond there to make it fully conjugated. But what do you think that does? I mean, I put a nitrogen in there, but does that change the count of pi electrons, do you think? It does not, because these are in an sp2 orbital. So they don't count as pi electrons, not pi electrons. And so you don't count them. This one still has the same number of pi electrons as the one we looked at on the previous board. You count 2 for every double bond, 2, 4, 6, 8, 10. That one contributes no pi electrons because there's a plus charge, and those don't count because they're outside of the pi system. So this is 10 pi electrons. It's a 4n plus 2 system. Aromatic when flat. Bless you. All right. Now, and things would change if I switch that carbocation carbon from a nitrogen to a nitrogen with the lone pair. Then all of a sudden the situation's different because it's got a different number of pi electrons. Then it would have 12 pi electrons and it would be anti-aromatic if flat, and it would want to be puckered. So lots of practice in the homework, so definitely take a look at those. When we come back on Wednesday, we're going to talk about carboxylic acids, and we're going to learn all about those. It's a pretty easy carboxylic acid chapter, so yeah, we'll start looking at that. Have a good day. Oh, remember, lab people, no lab meeting tomorrow for Chem 334. It's the Percy Julian documentary lab, so watch that, and that's your lab for this week. All right, see ya.